Hello everyone. Welcome to the course on hybrid electrical vehicles developed by Jawaharlal Nehru Technological University, Kakinada, supported by Andhra Pradesh State Council of Higher Education. I am Dr. Gudipudi Nageswara Rao, Professor, Electrical and Electronics Engineering Department at Lakkireddy Balireddy College of Engineering, Mailavaram. Hybrid electric vehicles are composed of different types of energy sources and power converters, which generally refer to vehicles consisting of an internal combustion engine ICE with an electric motor. Hybrid electric vehicles seem to be the most economically solution so far and probably for the upcoming decades. The general goal to develop the hybrid electrical vehicles is to reduce the fuel consumption and emissions while ensuring drives the power demands by investigating the appropriate energy management strategies. Energy management aims to obtain an optimal power split in view of complex driving conditions as well as to minimize fuel consumption emissions. It is commonly acknowledged that improvements in the fuel economy in hybrid electrical vehicles, thus the consequent reduction in emissions, depend crucially on their energy management strategies. Now coming to the powertrain topologies of hybrid electric vehicles. It is well known that there are mainly three kinds of topologies for hybrid electric vehicles: series, parallel, and power split. Coming to the series hybrid powertrain is regarded as a simple extension of a battery powered electric vehicle that is propelled by only motor. The engine drives a generator producing electrical power, which can be summed to the electrical power coming from the energy storage system and then transmitted through an electric bus to the electric motors driving the wheels. In principle, the advantage of the series hybrid powertrain is that only electrical connections between the main power conversion devices are required. Thus, vehicle parking and design are simplified. Meanwhile, the engine that is completely off the wheel offers greater freedom in the selecting the speed, loss, load, and thus allowing the engine to operate at a high efficiency region. On the other hand, the series hybrid powertrain requires two energy conversions, that is, from mechanical to electrical in the generator and from electrical to the mechanical in the motor, which result in a loss of efficiency even when there is a direct mechanical connection between the engine and the wheels in the existing configuration. As a result, in some cases, a series hybrid electric vehicles consumes more fuel than a traditional vehicle, especially in highway driving. Furthermore, one of the two electromechanical energy converters must be sized to meet the maximum power demand of the vehicle, as it is the primary source of the propulsion. And this slide shows the series topology. Coming to the parallel topology, the engine is connected to the powertrain by mechanical coupling device, while the motor propels the vehicle. Either engine or motor could propel the vehicle according to different load conditions, which makes it possible to greatly increase the fuel economy. The motor provides the power when the vehicle operates at low speed to reduce the fuel consumption. Thus, this configuration is capable of maintaining a higher efficiency and better fuel economy. The power summation is the mechanical rather than electrical, and the engine and the electrical machines, one or more, are connected with a gear set, chain, or a belt. Thus, their torques are added and transmitted to the wheels. In this configuration, there is no need to size one of the two electromechanical energy converters to meet the maximum power demand for parallel hybrid powertrain. However, unless it is significant oversized, the electric motors have less power than those used in a series hybrid powertrain, thus reducing the possibility of regenerative braking. Meanwhile, the engine operating conditions cannot be regulated as freely as in a series hybrid powertrain, since the engine speed is mechanically related to the vehicle velocity. Coming to the, as per the power split topology, the most important improvement is that ability to operate as a series, either series or parallel topology, which provides more operating modes to sustainably improve the overall efficiency under complex driving conditions. Although the series path is generally avoided because it is less efficient, the main feature of this design is that the engine, generator and motor speeds are decoupled, allowing additional freedom in control. The engine and the two electric machines are connected to a power split device so that the power from the engine and the electrical machine can be merged through both the mechanical and an electrical path, allowing series and parallel operations. Compared to the parallel hybrid powertrain, the power split architecture is the most flexible and represents a higher control ability on the engine operating conditions while adopting a double energy conversion, which is a typical of a series operation only in a small portion of the total power demand, thus decreasing overall losses. The power split topology is shown in this particular slide. Now coming to the types of hybrid electric vehicle architectures, and this slide shows the comparison. There are three main types of hybrid electric vehicles: series, parallel and series parallel. In series, hybrid electrical vehicles has no mechanical connection between the internal combustion engine and the wheels of the vehicle. The ICE is mechanically connected to an electric machine used as a generator that converts the rotational power of the ICE to electrical power. This electrical power is then converted from AC to DC through an inverter and stored in a high voltage HV battery pack. In order to use this electrical energy, a second inverter must be convert the DC power pack to AC, and the second electric machine used primarily as a motor converts the AC electrical power to torque that is sent to the wheels. The main advantage of this type of the hybrid electric vehicle architecture is that the ICE speed is completely decoupled from the vehicle speed. So the internal combustion engine can always operate at speed that allows for optimal efficiency. However, there is significant conversion losses that occur since the mechanical power from the internal combustion engine must be converted to electrical energy and then back into the mechanical power. These conversion losses reduce the overall operating efficiency of the vehicle. Coming to the parallel hybrid electric vehicles, do have a mechanical connection between the internal combustion engine and wheels. Typically, the internal combustion engine is connected to the wheels through an automatic transmission. An electric machine is also connected to the wheels somewhere along with the drivetrain. Commonly, the electric machine is connected to the drivetrain after the transmission on the same drive axle as the ICE. However, the electric machine can also be on a different axle known as the through the road hybrid or in front of the ICE, commonly referred to as a belted alternator starter. In this configuration, both ICE and electric machine can provide torque to the wheels at the same time. The vehicle can also operate as ICE only, electric only, or in a battery charge mode in which the electric machine charges the battery through regenerative braking or by absorbing torque from the ICE. Coming to the third one, parallel series hybrid electric vehicles are essentially a combination of the two previously architectures. In a parallel series, the vehicle can operate as either a parallel or a series vehicle. This necessity that two electric machines are used and that a drive train has a system to clutches that allow the ICE to be mechanically decoupled from the wheels. This architecture has the potential to be most efficient, but it is also introduces complexity in the mechanical drivetrain and overall control